This is review video 48. Why are some molecules likely to ionize and others aren't? So the first thing you want to remember is we're looking at this through the lens of acids and bases. So remember that strong acids and bases tend to dissociate or ionize completely, while weak acids and bases do not tend to dissociate or ionize completely, and that's not new information. So if we're looking at this equilibrium system right here, if I'm a strong acid or a strong base, I'm going to produce a lot of product, or I'm going to ionize more completely. But if I'm a weak acid or a base, I am not going to ionize or dissociate, and that molecule, be it acid or base, will stay together. Now, in terms of the what, the why, and the how, for acids and bases, it's a little bit different. It depends on what we're looking at. So for acid dissociation, that is going to be controlled by two main things, either bond strength, which is usually size related, or the stability of the conjugate base that forms once that acid loses a hydrogen. So if we're looking at simple acids, usually made up of hydrogen and one other atom, a monoatomic anion like chlorine or fluorine or bromine, we want to pay attention to the size of that anion. So the reason that we want to do that is all about Coulomb's law, because we know as the size of a particle increases, the distance between that particle and whatever it's attracted to is also going to increase. And when we increase our denominator, or that distance, we have a lower force of attraction. All right, so that's kind of the concept behind this. Again, we haven't talked about Coulomb's law in a hot minute. But if we look at these examples, it kind of starts to make sense. HCl, which is this one right here, is a stronger acid than HF is. I'm telling you that straight off the bat, but let's explore why. Chlorine is a much larger atom than fluorine is, meaning that its attraction to hydrogen, so the attraction between these two particles, is controlled by that size. Because if I look at the two distances between the middle of my atoms, I can see that the distance between H and F is smaller than the distance between H and Cl, even though it looks like both atoms are touching, because we're measuring from the middle of that atom. So that increased distance between H and Cl makes the bond weaker. In addition, we have to think about our electronegativity of our atoms. Fluorine is far more electronegative than chlorine is. So fluorine's attraction to hydrogen is going to be stronger, making it harder for that molecule to break up, whereas HCl can break up far more easily. So we say that the HCl bond is weaker, which makes it a stronger acid. Because if you're thinking about the strength of acids, we want to think about how easily can we produce H plus ions, or how easily can that molecule break up. Because if it can break up easier, it's going to be a stronger acid. Now, if we're talking about more complex acids, specifically acids that are made up of hydrogen and polyatomic ions or acidic hydrocarbons, we're going to look at some completely different things. Not size so much, but we want to look at the stability of the conjugate base we form, and we want to look at something called the inductive effect, which I'll go over in a second. So here's my example for you for your polyatomic ion acid, HNO3, or nitric acid. We can see the overall structure of HNO3 here. And for that molecule to be acidic, it means that this hydrogen right here has to be able to break off easily. And HNO3 can lose its hydrogen very easily. And there's a couple of reasons for that. The first is about resonance structures. So once that hydrogen leaves, we are left with just the NO3, and that is called a conjugate base. NO3 minus is a conjugate base that forms when that hydrogen goes away. And so when you look at the NO3 ion, we see that it has 1, 2, 3 valid resonance structures. Because remember, this double bond right here could be there, or it could be up here, or it could be over there. And since it can be in multiple places, that means that that negative charge is super stable because it can move around freely between those oxygen atoms. More resonant structures, so more ability for any double bonds or any charge to spread out, means that your conjugate base is going to be more stable, and means by extension that your acid can be stronger. So that's one thing to pay attention to. The other thing is something called the inductive effect, which is a little bit weird to think about, but the inductive effect has a fancy definition, which you can see over here. But basically what it is if you have a polyatomic ion that is made up of more electronegative atoms, then it makes it easier for hydrogen to break off. The reason for that is that electrons get pulled away from the hydrogen to ion bond. So in the case of nitric acid, it was the H to NO3 bond, right? And if electron density gets pulled away from that bond, it gets pulled towards the NO3. And if the electron density gets pulled there, it means that this H plus ion can just pop right off super easily, because all that electron density is kind of hiding in the center of the polyatomic ion. So let's look at two examples. We've got nitric acid, which I just showed you, and we have phosphoric acid over here. Two different acids made up of polyatomic ions. So nitrogen is a very electronegative atom. So the electrons that make up this bond right there, holding on the hydrogen, are going to be pulled this way. Those electrons get attracted to the nitrogen because the nitrogen is electronegative. And if those electrons that are holding that bond together are attracted somewhere else, hydrogen can leave really easily. Now, phosphorus, while also electronegative, is not nearly as electronegative as nitrogen is. So these electrons that make up this bond, they do get pulled, but only a little bit. So it's actually a lot harder for this hydrogen to leave. So once again, if you have a polyatomic ion that's made up of more electronegative atoms, that is going to be a stronger acid as a result. So all you have to do to determine that is to look at the electronegativity of your central atom on your polyatomic. Okay? Now, for base dissociation, again, that's a little bit different than acid dissociation, but not super different. Your base dissociation is all about either the ability to form a hydroxide or the ability to attract a hydrogen. So your bond strength would be between whatever your cation is to hydroxide, because we know that bases want to make this thing, and if we can make hydroxide more, we're a stronger base. That's very similar to our simplistic acids, because we want to look at the size of that cation to determine how easy this bond is to break. But if you're talking about Bronsted-Lowry bases, that's a completely different way to be basic, right? We need to attract a hydrogen ion to be basic in the Bronsted-Lowry definition. So our ability to do that controls our strength. So looking really quickly at the Arrhenius situation, our ability to form hydroxide, if we have a larger cation, just like larger anions with the acids, we're gonna have a stronger base. So between sodium and potassium hydroxide, well, potassium hydroxide is larger, and if we have a larger atom, then our attraction to the hydroxide as a whole is weaker. So this thing can break easier, making this our stronger base overall. In terms of Bronsted-Lowry, though, again, that is its ability to attract a hydrogen to itself. So there's two things you need to pay attention to. If that molecule has a lone pair of electrons, it's probably going to be able to attract a hydrogen. Why? Because electrons have a negative charge on them, and negatives are attracted to positive charges. So this attraction between those two allows that molecule, NH3, to pull a hydrogen. Now, If it doesn't have the lone pair of electrons, you can still evaluate it because if that atom or that molecule has more electronegative atoms within it, it's going to be better able to attract a hydrogen for the same exact reason. Because electronegative things have a slightly negative charge, which is going to be attracted to that positive hydrogen. So, looking at our two molecules here, we have NH3 and BH3. We can determine easily that this one is a stronger base. Why? Because it has a lone pair of electrons. That lone pair of electrons is immediately attracted to hydrogen. But again, even if it didn't, we would then evaluate the electronegativity of nitrogen versus boron and find that nitrogen is more electronegative, so this one would still be your stronger base. All right, now we have a practice problem. So this practice problem gives us two possible acids. We've got chloric acid, HClO3, and we have chlorous acid, HClO2. And it asks us which acid is stronger and why. So the first question you need to ask yourself is, what type of acid am I looking at? Is it more simple, made up of a hydrogen and one other atom, or is it more complex, made up of hydrogen and a polyatomic? And it's pretty obvious that we're dealing with hydrogen and some polyatomics here. So because I know that I'm dealing with hydrogen on a polyatomic, that means I need to pay attention to two things. One is the inductive effect. The second is the stability of my conjugate base. So if you recall, the inductive effect asks you to determine in the middle of your polyatomic, is there a difference in electronegativity? The answer is no, because the middle of our polyatomic in both cases is chlorine. And chlorine has the exact same electronegativity as chlorine, so the inductive effect doesn't matter here, not at all. So the only other thing we have to worry about is the stability of our conjugate base. And as a reminder, conjugate bases form when our hydrogen goes away. So our two conjugate bases are going to be ClO3 minus and ClO2 minus. All right, and so what I'm going to do is I'm going to redraw them so that we can just take a look. All right. All right, now I'm looking at my two conjugate bases, and yes, I omitted a bunch of electron pairs to just kind of simplify this drawing because I want to point a couple of things out. The first is what's going on with our double bonds. All right, so if we look at this one first, we see that there's a double bond on this side. However, that double bond could just as easily be over here. And what that means is there's two possible resonance structures available for ClO2. However, with this one, ClO3, this double bond could be here, or it could be here, or it could be here. This double bond could be exactly where it is, or it could be over here, or it could be over here. This single bond could be where it is, or it could be up here, or it could be over here. So what I'm telling you is that there's three possible resonance structures for that chlorate over there. As we know, based on the rule that I told you, the more resonance structures you have, the more stable you are. And the more stable you are, the stronger the acid. So that means that this chloric acid is my stronger acid because the presence of this extra oxygen stabilizes the conjugate base. If you have any questions about any of this, please feel free to ask me.